All right, so here's video number 4 for decision-making, confidence intervals versus probabilities, normals versus t's versus z's, etc. Problem number 8. Let's read it first. A random sample of weekly work logs at an automobile repair station was obtained, and the average number of customers per day was recorded. Compute the data following for this data. So here's our data. We'll have to plug that into our TI calculator to get some information on the sample statistics. We want to assume the number of customers per day is normally distributed with a mean and standard deviation calculated by the data. So the original random variable's number of customers is approximately normal. Small sample, therefore, going to conform to central limit theorem. What is the probability that 13 randomly chosen auto repair stations, the average repair time is between 23 and 25 minutes? So we're finding a probability, but this time average for 13 randomly chosen. So what this is that's asking the probability of x bar. So the probability that the average values, right, average, that's why it's x bar, so average, and then the x bar is between, oops, and I needed to put numbers on either side of that average, so x bar is in the middle, and it's between 23 and 25. So here are our values. And that's what we're finding here. This one is an average probability. So that is calling on the central limit theorem. So our n is equal to 13. Our mu, or x bar, it's actual sample information, so it really should be called x bar. Our S here is really here. Now we're going to assume that these are normally distributed with this mean and standard deviation, so even though we're going to be finding this, we're going to be using the normal distribution. And we don't find probabilities based upon the t. So we just use the normal distribution here, and so it's kind of like this is really our mu, and this s gets stands in the place of sigma. So even though this is actual, then we're saying we're just going to use those as stand-ins for these. So I need to calculate those values, so I'm going to input those into my calculator statistics data register, and then I'm going to find those probabilities. So I'm going to pause this while I do that, so not to waste time. Okay, so the mean calculated with my calculator is 23.8 when rounded one decimal, which is one more digit than the original data. Standard deviation, remember that I'm actually using the S sub x because this is a sample, not the sigma, and I'm going to use 1.5 for that. So now I have my mean and standard deviation that's going to be a stand-in for the mu and sigma, but these are actual data values. I'm going to have to standardize this. This is averages, so it's x minus mu divided by sigma over the square root of n. The sigma over the square root of n is because this is an average, right? This is the central limit theorem. So we're going to have 23 minus 23.8 and then divided by, and we have 1.5 divided by the square root of 13, and then we also have 25 minus 23.8, oops, 23.8, and then divided by 1.5 divided by the square root of 13. And we'll get those values, and then we're going to find normal CDF. And I'm just abbreviating that as norm CDF. And then we'll have the two values in between there, left bound, right bound. So calculating this, 23 minus 23.8 divided by 1.5 and then multiplied by the square root of 13. That's the way that I do that calculation, by the way, because the denominator of the denominator flips up and multiplies by the entire thing or by the numerator. So I get a negative 1.92 for this one on the left bound. So this is what I'm going to put in for this one, negative 1.92. And then on the right one, 25 minus 23.8 divided by 1.5, and then multiply that whole thing by the square root of 13. And I'm going to get 2.88 when it rounds. So 2.88. And then on my right hand side, 2.88 over here. And so normal CDF, and then left bound negative 1.92, comma, right bound 2.88, and that gives me 0.9706 when rounded. Now, if I were to do this using my normal table, remember I'd have to do a subtraction. I'd have to find the probability of being less than 2.88 and then subtract the probability of being less than negative 1.92. So we can go ahead and take a look at that and see how it would look. Remember, this is much more difficult. So if I go down here to my positive z table, 2.88, so 2.8, and this is my 88, I believe. Yes. There's my 2.88. This would be 0.9980. And then I would have to subtract the probability of being less than negative 1.92. So negative 1.9, it is. And then this is 0, 1, and this is 2. Let's just check that out to make sure. Yep, exactly. And so this is 0.0274, and so 0.9980 minus 0.0274 gives me the same exact value. That gives me the value here, and this would be using my z table. So you can do it either way. It's a little bit more complicated because we have to find the probability of a z being less than 2.88 and then subtract the probability of a z being less than a negative 1.92. But they give you the same probabilities. All right, now moving on to our last problem. So we have number 9. Let's read the problem. So problem number 9, the mean weekly salary of 45 randomly selected teachers is $1,350 with a standard deviation of $60. Give an estimate of the mean weekly salary of all such teachers using 95% confidence. Okay, so we have the estimate of the mean weekly salary, and that says all such teachers, we're finding a confidence interval. And that's further emphasized by the fact that it says use 95% confidence. So we're finding a 95% confidence interval, and we're doing it for the mean. Now we need to investigate. Our n is 45, right? Because it says the salary for 45 randomly chosen teachers. So n's 45. So this is greater than 30, and therefore we're going to use a z critical value. So my z critical value for a 95% confidence, that is going to look like putting 0.95 here in the middle, and the 0.5 split up in each of the tails. This is going to be 0.025, and the same over here, 0.025. And so these critical values, these z's, the minus on this side and the plus on this side, and that's going to be found from the inverse and then normal and 0.025. 5. Now this one's going to give you the -1, but we don't care about the sign. Now you may have that already memorized, that this is 1.960, or you may have to look it up, and if you do it, second function distributions, inverse normal 0.025, you're going to see a -1.95996, which rounds to 1.96. So now we have our critical value. We're going to start out with our X bar, our sample mean, which is $1,350. And then we need our standard deviation of that sample, which is $60. And furthermore, we are going to give this confidence interval in the following way: 1350 plus or minus my critical value, 1.96, multiplied by my standard error, standard deviation, divided by my square root of my sample size, 45. So we will get, first of all, a margin of error calculation. I'm going to do 1.96 times 60, and then I'm going to divide it by the square root of 45. So now I have 17.53 as an approximation here, and I'm just going to round that to 17.5, since how everything's in whole dollars, so I only need tenths to be one more decimal than the original. So we have 1350 minus 17.5 for my left side of the interval, and for my right, plus the 13.5. So I'll write it down here again. So 1350 minus 17.5, we have 1332.5, and these are in dollars. And then the plus the 17.5, and that's going to give me 1367.5. And interpretation of this is, with 95% confidence, we feel the true mean weekly salary of all teachers is between $1,332.50 and $1,367.50. And so that wraps up these examples. And hopefully you got them all right, or at least you learned what you missed when you were looking for them so that you could get the correct answers.